In this video, we're going to look at the classification of matter. Now, before we begin to understand anything in chemistry on a deeper level, it's going to be important to understand how matter is organized. So matter, just to give you the general definition, even though I'm sure you've heard it before already, matter is defined as anything that has mass and takes up space. So anything that can occupy a particular volume, no matter how small, is defined as matter. Now, matter primarily exists in three different states, three different phases, if you will. Those three phases are solid, liquid, and gas. So I have a picture here that shows a penguin floating out at sea, and he's obviously floating on liquid water, right? So the sea, the ocean, would be the liquid water. The iceberg in the back and the iceberg he's standing on would be solid ice, right? So solid water. And the vapor in the air would be gaseous water. Now, these are three macroscopic ways that matter presents itself that are all different because of the way that the matter is on a microscopic level, on a molecular level, right? So let's talk about a solid first, right? So solid. So thinking about ice, or really thinking about any solid object, solids have a very rigid structure, right? So solids are, matter that has a very rigid shape. And why does it have that rigid shape? Well, when we look on a molecular level, so looking at this molecular level picture, which are in all of these circles, for the solid, when you have solid water, the water molecules are very rigid, they're locked in place, and they don't move around very much. And that's why most solids have these very rigid shapes, because on a molecular level, the molecules aren't moving that much, so if at all. So on a molecular level, these solids, the molecules are locked in place. So I'll say the molecules are locked and close together, right? So they're very tightly packed and they barely move. And that's very characteristic of solids on a molecular level. Now let's go to liquids. So for liquids, they have a definite volume, but their shape, they can take on any shape of whatever container they're in, right? So if you have a gallon of water, if you have it in a water jug, or if you have it in, some sort of straighter container, it's going to take on the shape of that container. So it has a definite volume, but variable shape. Right. So what this means is liquid is very flexible, right? Liquids are flexible. They have a definite volume, but they can take on any shape. So they're a bit more of a flexible structure. And when we look on a molecular level, the molecules are more spaced out. So they're not as tightly packed as compared to a solid, and they move around a little bit more, right? So molecules are close, but move to some extent. Right? So in the case of a liquid, we have molecules that are close together, but they're not as close as a solid, and they actually have more freedom to move around a little bit more. Right? So in a liquid case, you have a little bit more of a flexible molecular structure, which manifests itself on a macroscopic level as a more flexible macrostructure as well. And the last one we're going to look at are gases. Right, so for gases, this is really no hold bars. They don't have a fixed volume, nor do they have a fixed shape. So no fixed volume or shape. Right, so you can put a very small amount of gas in a large container it's going to take up the entire container, right? Or you can put it in a very small container and compress it. It'll take up the volume of that small container. So it is really flexible. And the reason why is because the molecules are so far apart, spaced so far apart, and they move very randomly and move a lot, right? So you end up with a molecular structure where the molecules are far apart and move randomly, right? So it's very, the molecules are moving around a lot faster. There's really no rigid structure to gas molecules, right? So you really run the gambit of molecular interactions here when you're talking about the difference between solid, liquid, and gas. You go from a very rigid, locked structure with a solid to a more randomly distributed, more, random motions with gas particles versus solids, right? So these are the three main ways that matter presents itself as far as being able to classify what phase the matter is in. Now, there are more ways that we can classify matter, and at this point, I want to introduce a little bit of a flow chart where you can make certain decisions to show how you're going to classify matter. So let's start at the top of the flow chart with matter, right? So if you've identified something in the world that has mass and takes up space, and you want to more specifically classify it, the first question you want to ask yourself is, can you physically separate that matter? Do you see two different components that you can physically separate? So the first question you want to ask is, can it be physically separated? And that's not just limited to, can you actually, pick off different components? There are certain scientific techniques that are also physical separation techniques that you can do, even if you can't physically pick out certain aspects of the matter, right? So if the answer to this question is yes, right? So let's say you answer yes to this question. You see different components. They can be physically isolated. They can be physically separated. Then that means you have a mixture, right? If you can physically separate it, then that means you have a mixture. If you cannot physically separate it, you answer no to this question, there's no way you can physically separate the different components of this matter, that means you have a pure substance. Right? So, for example, if you have some mixture of oil and water, right? You can see those different components. You can physically separate the oil from the water. That's a mixture. If you have like a titanium block, right? You can't separate anything. It's only made of titanium. It's a pure substance, right? Okay, so let's focus in on the mixtures here. So if you've identified your matter as a mixture, you see it can be physically separated, you can ask an additional question in order to add more specificity into what type of mixture you actually have. So the question you're going to want to ask is the composition of your mixture uniform? So is the composition uniform? Right, so that just means, can you actually see any differences in the components of your mixture? If your answer to this question is no, if the composition is not uniform, then that means you have a heterogeneous mixture. Right, your mixture is heterogeneous. That means that it's not uniform throughout. You actually can see different components in the mixture. If the answer to this question is yes, the question is the composition uniform? If your composition is uniform, then that means you have a homogeneous mixture. Right, so these are the two different types of mixtures that you can have, either a heterogeneous or a homogeneous mixture. Now, taking our attention to pure substances, The question you want to ask to be able to further classify a pure substance is, can it be chemically decomposed? So can it be chemically decomposed? Right, so in one of the previous videos, we looked at a chemical process that decomposes water into its elemental components. You run an electrical current through water, you can isolate the hydrogen from the oxygen. So that's what I mean by being able to chemically decompose something. Can you do a chemical reaction or some kind of process that can decompose the compound from its elemental components? If you can further decompose it chemically. So if your answer to this is yes, we can decompose it chemically, that means you have a compound. Right? So a compound is a molecule, right? It's something that's composed of multiple different elements. If you cannot decompose it chemically, if the answer to that question is no, then you have an element. Right, so once you've broken down water into its elemental oxygen and hydrogen, you can't break down those elements any further. But water itself is a compound because you can break down the water, into its hydrogen and oxygen components. So you can use this. This is basically a decision tree. And you can use this this matter decision tree in order to decide whether what you have is a mixture or substance, and to be able to classify it even further from there. So let's look at some example problems so we can put this into practice. So the first problem says white gold used in jewelry contains two elements, gold and palladium. Two different samples of white gold differ in the relative amounts of gold and palladium that they contain. Both are uniform in composition throughout. Without any other knowledge about this material, how would you classify it, right? So the first thing, we want to go back to our decision tree so that we can decide what type of way we'll classify this matter, this white gold. So it's composed of gold and palladium. And if you're familiar with these metals, these can be melted down and physically separated. So we would answer yes to this first question. Can we physically separate the gold from the palladium? The answer is yes. We know that we have some sort of mixture. Now, in the question, it does answer this second question of, is the composition uniform? So it tells you both are uniform throughout, right? Any different mixture of white gold is going to be uniform in its composition throughout. So that means we answer yes to this question. So we get to our final determination here that white gold would be a homogeneous mixture. So let's write this in here. So white gold would be a homogeneous mixture. Okay, cool. So yeah, we basically just use the decision tree in order to decide what way we would classify the matter, and we'll classify it as a homogeneous mixture. Okay, so the second problem says aspirin is composed of 60% carbon, 4.5% hydrogen, and 35.5% oxygen by mass, regardless of its source. How would you classify aspirin? So when we're dealing with aspirin, we're talking about the elemental components that make up aspirin. Those can't be physically separated. So you can't do some physical separation technique and be able to separate the carbon from the hydrogen from the oxygen. So we would have to answer no to this first question. Can it be physically separated? No. So that means we have a pure substance. So then the second question is, can it be chemically decomposed? Well, we know the answer to that question is yes, since we know that it's composed of carbon, hydrogen, and oxygen. It has these elemental components. So we answer yes to that question because we know it can be chemically decomposed. So that means aspirin would be classified as a compound. Right? So we know that it's a pure substance and we can classify it as a compound. Now, earlier I mentioned that physical separation doesn't just have to be, can I pick different elements of this mixture apart, or can I, separate it with my hands, right? There are other physical techniques that we use in chemistry in order to separate mixtures. And these are two. So the first one that you see here, this is called vacuum filtration. So vacuum filtration, the basic idea behind vacuum filtration is that you have some heterogeneous mixture where you have a solid and a liquid in the same mixture, but the solid is not dissolved. It's still clearly there. What you can do is you can set up a flask and put what's called a Buchner funnel into the flask. The flask is attached to a vacuum that's going to be able to create a vacuum in the flask and start to suck on this Buchner funnel. You put your mixture into the Buchner funnel, and what's going to happen, you have some filter paper here. And so what's going to happen is that the vacuum is going to suck through the water, so the liquid is going to come through the flask, and the solid is going to still be at the top on your filter paper, right? So you're basically separating the solid from the liquid using a filtration technique. This is also a physical separation technique, right? So, so again, even though it's not a technique where you're just physically separating stuff with your hands, but this is also a physical separation technique. The other technique is called distillation. So this figure on the right shows a general distillation setup. And this is a really cool technique. So basically what you do is you put your sample here in the distilling flask, you heat it up, and the idea behind this is that your two components, this will be a homogeneous liquid solution, and your two components have different boiling points, right? So different points at which they would boil and turn into a vapor, right? So basically what you do is set the hot plate to the boiling point, or set your solution to the boiling point of one of your components, right? So that component boils off, its vapor goes up this tube, and then the vapor will hit a condenser. This condenser is at a very cool temperature, so it's going to cool back down that vapor, turn it back into a liquid, and then arrive in this receiving flask. So you're separating the two components based on the differences in their boiling points, the differences at which they boil and become a vapor. So these are two physical separation techniques that may not be exactly obvious that they're physical separation because you're not physically touching the system, but these are physical separation techniques. So hopefully this gives you a good idea of how to classify matter, and a few examples of how we can separate different matter physically and chemically, and use those to decide what we can classify matter is in a very specific way.